designing of the mold. It's simply a calculation of the dimensions required for the final design purpose. Okay. Before that, we have started with the different aspects required for the designing of the compression mold, starting from ejector pin and why the requirement of heating and venting, then basic design parameters like projected area, bulk factor, clamping force, land dimension, and the ejector pin length. So we have seen in detail about these things, so like bulk factor, the ratio of raw material or the raw molding compound to the final product, volume of the final product. Okay, that's how we define the bulk factor. While defining the bulk factor, we have added the flash allowance also, around 10 to 20% flash allowance. Basically, by using the bulk factor, we are going to calculate the volume of the loose powder or the volume of the raw material required to manufacture the particular plastic component. Okay, by using the design parameter, we can easily calculate the volume of the component before without manufacturing also. But we need that for the particular component or for the manufacturing of particular component, how much quantity of raw material is required. Okay, and for that we are using this bulk factor. Then we have seen the projected area also, right? This is the effective area over which we are applying the compressive force. Wherever there are transparent or through holes, we are reducing that area and we are getting the only effective area. Then clamping force refers to the force applied to clamp the mold, okay, or to just make the molds very close to each other. So there should not be any gap, otherwise the heated raw material will try to escape from that gap, or there is a possibility of trapping of gases also. Okay, so that clamping force is that force which makes the two molds uh, to clamp together. Okay, that is the force. That force is the clamping force. Right. So it depends upon the projected area of the molding. Depending on the projected area and the pressure that is applied from the top, that will decide the clamping force. Okay. Land dimension is the difference between the actual cavity and the vertical wall of powder well. Okay, that's how this land dimension we discussed. And then we started with the just looking after the basic process and various allowances, considerations, assumptions. Okay, because most of the times whenever you are solving any kind of design problem, at least 30 to 40% parameters are assumed. Okay, more around 30 to 40% assumptions are there, and based on that assumptions we are calculating the dimensions approximately. Okay, not the exactly. Okay, but at least we get the range. Okay, and we are based on that range we are using the tolerance and allowance. Okay, and with that we are designing the component or the mold. Now here in the last lecture we'll just revise. So we have seen the actually basic process or the basic steps which are required to design a compression mold. Okay, so the first factor was the bulk factor, and the formula is simple: volume of loose powder, volume of the loose powder. Okay, powder, or it may be pellets, or simply a volume of loose material to the volume of product. That is nothing but the bulk factor. Second one was, I'll zoom it. Okay, second one was the land dimension. Okay, land dimension. Okay, so in the land dimension we have seen that generally these are the assumptions. If there is a normal size mold, land dimension is considered as 4 to 9 millimeter. Okay, length of the land dimension, or in case of large size mold it is around 9 to 16 millimeter. If nothing is mentioned, you can take it average one. Then we have seen the design of loading chamber. Okay, so this is the basically loading chamber. You can easily calculate the dimensions. Okay, so this is the loading chamber, the chamber in which the actually product or the raw material is compressed. Okay, so though we required, suppose for example, this kind of product exactly having the vertical walls, but if we'll prefer this kind of mold only, then it is very difficult to remove this component out of the mold cavity because of this vertical surface. It will stick to the inside internal surface of the mold. Okay, so that we are giving this flare allowance. Okay, so this is nothing but the simple this angle we are providing. Okay, so there is a angular this variation. Okay, so this variation is around 0.33 to 1 degree. This is called as a flare. Then depth of loading chamber. Okay, this is the one of the important formula. Just keep it in mind. Depth of loading chamber is calculated by this way: volume of loose powder or the raw material minus volume of cavity divided by projected area. Okay, volume of loose powder minus volume of cavity divided by the area of projection or the projected area. And then we saw the how to calculate the projected area. Just now here, if you see, this is a cross-sectional view of the component. So here it is a completely through hole. Okay, this is a through hole, through cavity. Okay, transparent cavity. Okay, so we are not considering this area, this cavity area. Okay, we are considering only this much area. Okay, and this area is called as a projected area. How to calculate? Just get the total area and reduce this much area. You will get the projected area for that particular component. Then flash thickness. Okay, I told you the flash thickness is mostly considered as flash allowance. Sorry, flash allowance will be considered as a 0.13 millimeter. Okay, if not given directly, consider flash allowance as 0.13 millimeter. What is the flash allowance? Whenever this raw material will be there inside the cavity, and when you will try to push this top mold, or will try to compress this raw material inside this cavity, some material will try to escape from this. Some material will try to escape from this cavity. Okay, this way, in this direction. Okay, this way and this way. So this material will be trapped on this land surface. This material will be trapped on this land surface. Okay, so it will be compressed on this area, land area. Okay, actually it is required to compress in this area only, okay, but it is getting compressed here. So this extra material which is getting compressed over the land surface is called as a flash. It's called as a flash. You can remove it, as it is not going to be a part of final component. You can remove it in the finishing operation. Okay, generally there is no as such calculation for the flash. Just take it that flash allowance equal to 0.13 millimeter. Okay, right. So then clamping force. Okay, then we have seen the clamping force. Right. So clamping force is nothing but the, as I told earlier also, this is the compression pressure which will be given in the problem. Projected area you can easily calculate by reducing the cavity area if it is a through cavity. Okay, just multiply compression pressure with the projected area, you will get the clamping force. Okay, compression pressure, if not given, mostly it will be given. If not given, look at the material for the raw material. If it is a phenolic material, you can take the average of this 158 to 211. Okay, and if it is a melamine material, you can take the average of this compression pressure. Mostly in 90% cases it will be given in the problem. Okay, so you can directly take down, just you need to calculate the projected area. Then we have seen the ejector pin. Okay, basically ejector pin is a simple pin like this in this way. This is going to be a pin in this way. Okay, here will be a holding base, and here will be some kind of shape, maybe like this, maybe like this also. Okay, depends on the surface of the component over which we are putting this ejector pin. Okay, so basically length of ejector pin is bifurcated into three categories: L1, L2, L3. Okay, L1 is the length in contact with the mold plate. You can easily calculate it by using this formula, 5 into thickness. Okay, thickness of the product. Okay, product thickness or the wall thickness of the part. Getting? Okay, so 5 into that wall thickness, you will get the L1. Second, ejector stroke will be given in the problem, or else there is a one more method. If suppose this is the component you are going to manufacture. Getting it? Okay, so for this you required a mold of such size or lesser size, but this shape. Okay, so in that case, see, this size product you have to take out from the mold cavity by pushing from this direction. Getting it? Okay, so how much you will have to push? at this much depth, okay, with this height. Okay, so whatever with this size, that much ejector stroke is required, and small allowance is required, that is a 5 millimeter. Okay, by this way you can calculate the ejector pin length also. Right, now we are having one problem, and we will try to solve this problem. You can easily understand the things. Okay, just read, I will write down some couple of more information. Okay, bulk factor we have considered, compression pressure we have considered 90. Okay, and density. So this is 90 kg per centimeter square, and then one more thing is required is density. Okay, density is 1.79. density is 1.79 gram per centimeter cube. Okay, gram per centimeter cube. What is required? Product. Okay, product is required. Okay, so let's see, just see here now. Design a compression mold for a component as shown below. Okay, I'll draw the component also. It is made up of melamine material. Okay, with this melamine material you can take compression pressure, but no need to worry about that. Compression pressure is also given, bulk factor is also given, and density is also given. Okay, just we need product. Okay, so product is of this size. Just a minute, I'll try it. Okay, it should not be a sharp corner, it should be right. Okay, the lines are exactly vertical. Okay, kidding. Okay, so just this is the simple and easy product, right? So for this kind of product we have to design the compression mold. Okay, I'll give the dimensions also. So this complete diameter is 4 centimeter. This entire height is, this is 2 centimeter, and this thickness is also 4 millimeter. Okay, and one more thing, here there is a, it is not a exactly corner, so this is a r equal to 2 millimeter. Okay, radial shape is there, right? So now if you see, a very simple product is given, and for this kind of product we'll have to manufacture, or we'll have to design, sorry, we'll have to design a compression mold. Okay, so this is simple kind of like cap. Okay, a bottle cap. Okay, like a bottle cap. So it's, see this is the a complete diameter is a 4 centimeter. Thickness of the wall of the component is 4 millimeter. Height of the component is 2 centimeter, and this, there is a radius of 2 millimeter is provided at these corners. Okay, not the corners, at this juncture. Okay, so we'll start solving the question. Okay, just before that, we will write down the given data. Okay, okay, easy to solve. Okay, now only three things are required: bulk factor, compression pressure, and density. Okay, and these component dimensions. Right. So what is given in the problem? Bulk factor. Bulk factor is, just a minute, bulk factor, that is a K, we denote it by K. It is given as 2. Compression pressure, okay, we have denoted this as by Cp. Compression pressure is given as 90 kg per centimeter square, and density is given as 1.79 gram per centimeter cube. Okay, very easy components. In your exam also there will be this kind of simple components will be there. Getting it? Okay, now just a minute, this we have denoted with the help of not Cp, we have taken this as a compression pressure Pc. Okay, now this given data we have written. Okay, we will follow exactly the same procedure what we discussed. Okay, from this part we have started discussing the process. Okay, getting it? Okay, bulk factor directly given, bulk factor directly given. Okay, now from this bulk factor, what you can calculate? Volume of loose product, sorry, loose powder and volume of product. Now if you want the volume of loose powder, you need the volume of product, you need the volume of product. Okay, right now, now if you see where it is. Okay, now in the design of this product, everything is given: diameter is given, height is given, this entire counter radius is given, size, wall thickness is also given. Okay, so the first part, one by one, in the same way what we discussed, a similar way will go. Bulk factor, the first part was bulk factor, K equal to volume of loose powder divided by volume of product. Okay, here we know bulk factor. Okay, we can calculate volume of product. Okay, so let's calculate the volume of product, because we want the volume of loose powder, volume of product, volume of product. Okay, getting it? Okay, now let's see here. If you see this figure, or else I'll just draw it once again here. This size is 4 millimeter, this height is 2 centimeter, and this diameter is 4 centimeter. Getting it? Okay, so this is the simple and easy product. Okay, now we want to calculate the volume of product. Right, volume of product. Okay, so very simple, easy to calculate the volume of product. Now what we will do, the larger diameter will take it as D1 and smaller diameter will take it as D2. Okay, we want only the volume of product. Okay, so where is the material consumed in the product? See, these two walls and this base. Okay, so this is a, if diameter is given, that means this is a cylindrical product. Okay, this is a cylindrical product. It's simply as like a bottle cap. Okay, bottle cap. See, so first of all, I will calculate the volume of this vertical walls. I will calculate the volume of vertical wall, and then I will calculate the volume of base, because base is a different part and the this side walls are different one. Getting it? Okay, so first of all we will calculate the volume of the pi by 4. Okay, so this vertical wall volume, this larger diameter we are taking as D1 and smaller diameter we are taking as D2. Okay, larger D1, smaller D2. Okay, so volume of D1 square minus D2 square, this is the area. Getting it? This is the area into height into height, or rather we'll call this as a length of the product. Okay, this one. So d1 square larger, d2 square smaller. Okay, only this wall thickness will be considered in the volume of product. Plus i need the volume for this base. I need the volume for this base also. Okay, so we have to calculate the volume for this base also. Okay, now diameter is 4 centimeter, and just a minute, diameter 2, 3.2. okay, right. So here pi by 4. Okay, now if you see the vertical part, this vertical part we have considered in the wall only, this much up to this one. Okay, so we need to consider only from this area to this area. Are you getting? Okay, so this only volume we required, because this is we have considered or covered in the vertical volume. Okay, so this is nothing but, if you check out, here is the d2, here is the d2 exactly. So this will be d2 square into t1 or t, this thickness. Okay, t1 or t, or simply you can consider this as a thickness. Okay, so this thickness of the entire part is same one, 4 millimeter is given. Okay, we'll calculate now volume. Okay, so this pi by 4, what is the larger volume? So the larger diameter 4 centimeter. Okay, 4 square minus smaller diameter. Okay, if you check out, it is 4 and 4 8, so it will be 3.2 square, and length is 2 centimeter, so it will be 2 centimeter plus pi by 4 t2 square means 3.2 square, and wall thickness is given as 4 millimeter. We required it in a centimeter, 0.4. Right. Okay, so there is nothing difficult. These are simple calculations. Actually, we should not take this much of time. Simple thing. First of all, the volume of the vertical walls, and then the volume of the base. Okay, finally pi by 4 d square into length. Okay, effective wall thickness just you have to consider d1 minus d2, and then the volume of the base. Okay, so totally if you will calculate this, now I will not, just a minute, let me calculate. 4 square minus 3.2 square into 2, and this will be addition. Okay, so this will come out as pi by 4 into 3 minus 2 square into 12.264 centimeter cube volume of product. This will be our first part. Okay, so any problem you will get the first part, that is the calculation of volume of the product. Okay, whatever, just try, just take care you will calculate the proper volume, because possibility that you will mistake, like here instead of 3.2 you may take as a 4. Okay, don't make that small mistake, because this diameter we have considered in a larger part only. Okay, in the vertical section only, so no need to consider once again that. Okay, so effective base only we have to consider. Okay, so first part we got, that is the volume of the product, that will be 12.264 centimeter cube. Okay, and just take care of the units also, right? Now the second part. Okay, if you check out here, bulk factor we know, volume of product we know. Now we can calculate easily volume of loose powder. Okay, volume of loose powder. So that will calculate Here only I'll do that. Capital K is equal to volume of loose powder divided by volume of product. Okay, so volume of loose powder divided by volume of product is 12.264 centimeter cube, and the value of K is given as 2. Okay, value of K is given as 2. So if you calculate volume of loose powder, okay, so 2 into 12.264, 2 into 12.264. Okay, now whatever it may be, it will come around 25 centimeter cube. Okay, but is it a correct one? Is it a correct one? Okay, I'll take back you to original part. Check out here what we have written. The loose powder volume, what we are considering as VLP, is equal to, this is nothing but our ratio. Okay, this is nothing but our ratio, 1.1 into, sorry, 1.1 to 1.2. This flash allowance we have to consider. This flash allowance of 10 to 20% we have to consider, and then only we'll have to get calculate the exact volume. Okay, so apart from this 2, we'll have to multiply it by 1.1 or 1.2. Okay, 1.1 or 1.2, we'll take it as a 1.2. Okay, if you take 1.1 or 1.15, that will not be again mistake. Okay, your just answers will vary. So we'll take this as 1.2 into K into volume of product. So 1.2 into K is equal to 2. Volume of product is 12.264 centimeter cube. Got it? This 20% is the flash allowance that we have considered. Okay, so it will come around, now it will increase, 12.264 into 2 multiplied by 1.2, so it will 29.435 centimeter cube. Okay, this is the first answer. Okay, this is the volume of any problem, any type of problem, you will have to calculate first of all this one. Okay, volume of the loose powder, volume of the loose powder. Now second one, your first calculation is this one, volume of product. Second calculation is this one, volume of loose powder. Okay, now the third one. Okay, so third one is the calculation of land dimension. Land dimension, we are following the same steps that we discussed while giving the formulas. Okay, now land dimension, if you check, we have simply given that as an assumption. Okay, so land dimension, it is, see, if nothing is mentioned, just assume it. It is assumed as 13 millimeter. Okay, looking to the, you will have to mention one more line. Looking to the design of component, land dimension is assumed as 13 millimeter. Okay, this will be a standard value. This will be a standard value for the land dimension. Any kind of problem, just consider this as the specific one. Okay, now projected area. Fourth is projected area. Okay, projected area. Okay, very easy. Your very simple calculations are there. Now in the explanation, we have seen this product. We saw this one product. Okay, and in this case, we had considered the projected area as total area minus this area through cavity area. Okay, now our product is different one. Our product is like this. Are you getting? Okay, so here there is a base. Here there is a base. It is not the through cavity. It is not the through cavity. Okay, it is not simply like this. If it will be like this, we may have taken the area of only walls, only vertical walls. Okay, but now this time there is a base. There is a solid base at the bottom. There is a solid base at the bottom. Okay, So this is the exact product. This is the exact product. Okay, there is a solid base at the bottom. Okay, so and what is the diameter, complete diameter? This is a 4 centimeter diameter. Okay, there is a 4 centimeter diameter. So that effective part we have to consider. Okay, so simply projected area will be pi by 4 d1 square. Are you getting my things? Okay, don't think it in a way that why this open space area has not deducted. Okay, it will be deducted when this solid base will not be there. Okay, so now this is going to be a part of component, this solid base is going to be part of component, so this is going to be an effective area, right? I'm destroying this. So this will be your effective area pi by 4. What is the d? 4. It will be 4 square into pi by 4. So let me calculate this. Okay, so this is coming as 12.56 centimeter square. Okay, so this is nothing but the AP is 12.56 centimeter square. Okay, this fourth part we got, this was the third part. Okay, volume of product, then volume of loose powder, then flash allowance, then land dimension, and then projected area. Okay, then projected area, getting it? Okay, now the next one, what is the number? Fourth. Fifth one was depth of loading chamber. Depth of loading chamber. Okay, and this we have nominated with capital T. Okay, and we have seen the formula as volume of loose powder, volume of cavity, and divided by projected area. Okay, volume of loose powder minus volume of, sorry, chamber, volume of loose powder minus volume of chamber divided by projected area, Okay, now okay, now if you see this, we know this volume of loose powder, we know the area of, sorry, projected area, but we want this volume of chamber, okay, chamber for the mold, volume of the chamber for the mold. Okay, so let's calculate it. What is the product? What is our product? This product is of this size, getting it? Okay, this is the height of the product or the length of the product, and this is the width of the product or the diameter of the product, getting it? Okay, this is the simple product. Okay, so this kind of mold only required. So how mold will come? This mold will be outside this. Are you getting? So this is our mold size. So this is the chamber, this is the only chamber, getting? Okay, right? So size of product will only decide the volume of chamber, getting it? Okay, so we want to only calculate the volume of chamber. So volume of this only will the volume of chamber. See, this cavity is also going to be a part of chamber. Okay, chamber is that section where we are putting the raw material, so volume of chamber, being a cylindrical product, pi by 4 d1 square, this is the area, and length, this will be the volume. So it will be pi by 4 d1 square is a 4 square into 2, pi by 4 square into 2. Just let me calculate. This is coming as 25.13 centimeter cube. Okay, 25.13 centimeter cube. Okay, so now easily based on that we can calculate the depth of the loading chamber. Volume of loose powder minus volume of chamber divided by area of, sorry, projected area. Volume of loose powder, where it is. Here it is the volume of loose powder, 29.435. Let's take it. 29.435 minus volume of chamber. Here it is. 25.13 divided by projected area. Here it is 12.56. 12.56. Okay. If you calculate this, then 1299.435 minus 25.13 divided by 12.56. So it will be coming as 0.34 centimeter. Okay, so depth of loading chamber will be 0.34 centimeter. Let me check calculations once again. 29.43 minus 25.13 divided by 12.56. 0.342. Okay, so 0.342. Okay, so that is okay, no problem. So that will be a depth of loading chamber, right? So this part also we got. This is the fifth number, right? So land dimension, projected area, depth of loading chamber. Sixth one, same direction we are going. What is sixth one? We will check once again in our description. Compression force, flash thickness, same number, flash thickness, sixth one, flash thickness. And what is, if not given, here is the number, okay, take it. Flash thickness, nothing is mentioned about flash thickness. Is assumed as 0.13 millimeter. Getting it? Okay, if nothing is given, whatever we have assumed, same way you can consider. Okay, then seventh, clamping force. PC or CP. Clamping force. This is, I think, compression pressure. So clamping force FC. Let's take as clamping force FC equal to, what is the formula we have seen? Compression pressure into projected area. Compression pressure into projected area, that will give you the exactly clamping force. Okay, so what is the compression pressure? Let's take out the problem. 90 kg per centimeter square. It is 90 kg per centimeter square. And what is the projected area? Where it is projected area? Okay, 12.56 centimeter square. It is 12.56 centimeter square. 90 into 12.56 centimeter square. So it is coming as 1. Let me check. 90 into 12.56. 1130.4. Okay, where is the pressure? It is kg per centimeter square, and area is in centimeter square. So centimeter square is cancelled. It will be kg. Okay, force will be kg. Okay, don't get confused with units. Okay, CGS system is used here. Okay, so clamping force is also over. Now what is remaining? Clamping force is over. Ejector pin, the last one, the ejector pin. Okay, and one more is there. So we'll calculate the length of ejector pin. So this is eighth one. Length of ejector pin, capital L P, equal to, we know the formula, L1, L2, L3. Okay. Out of this, L1 is equal to 5 into dP. Okay. This we have seen. This is the stroke. And I told you, if this is the size of product, okay, this is the height of product, this much, by this much length we have to push it so that it will be completely removed out of the mold. Okay, by this much. Okay, depending on the height, it will decide the stroke. And this is the allowance. This is the allowance. Let's calculate one by one. L1 equal to 5 into product thickness. 5 into product thickness. Okay, so what is the product thickness we have considered? It is given in the product. Check out, 4 millimeter. Okay, this one thickness of the product, everything is given. So 5 into, we are calculating everything in a centimeter, so it will be 2 centimeter. Okay, it will be 2 centimeter. Now L2, ejector stroke. What I told, the stroke, what is the meaning of stroke? Stroke means by how much length or by how much distance you will have to push that pin, so that product will be completely out of the mold. Okay, let's check out here. See, this is the size of the product. Okay, the mold will be around this. So height of the product is 2 centimeter. So you will have to start pushing from this end, and you will have to go on pushing up to this point, and at this point this base will be at this surface. Okay, and it will be exactly come out of the mold. Okay, so this is the length by which we'll have to push out the product from the mold cavity. Okay, this is the pin. Getting it? Okay, so the length of the product or the height of the product will decide the stroke, ejector stroke required through the ejector pin. So what is the, forgot to see. Okay, what is the height of the product or the length of the product? It is 2 centimeters. So exactly L2 will be come out as 2 centimeter. Okay, we got the L1, we got the L2. Okay, now L3 we have taken as allowance. This allowance was given as 5 millimeter, so it will be 0.5 centimeter. Okay, we got L1, we got L2, we got L3. So LP is equal to L1 plus L2 plus L3. So it will be 2 plus 2 plus 0.5. Okay, so it is around 4.5 centimeters. So LP will be 4.5 centimeter. Okay, so this is the length of ejector pin. Have you got the things? Okay, simple. Okay, everything is given, you will get it very easily. Okay, are you getting right? Okay, and the last one. Okay, dimensions of punch, because punch is required to compress the material inside the cavity. Okay, now look here carefully. Okay, this is the product. Are you getting? And the complete size is 4 centimeter. This is 4 millimeter. Okay, and this one is 2 centimeter. Okay, this one is 2 centimeter. Right? Okay, so initially there will be mold cavity as like this, and the material will be poured inside this. Now there will be a punch. Okay, so if this is the size of the product, see how this is going to happen. I will exactly show you. Material will be inside this cavity. Okay, this punch will come from top. This punch will come from top. Okay, and this will compress the material. So material will be compressed like this. Material will be compressed like this. At the start, it will be completely filled. Okay, and then it will be compressed around this punch, below and around this punch. Are you getting meaning? Okay, so this is the area where this material is getting compressed, and that's what that's what's the exactly shape we want. I will show it with this. Just if you can imagine it, it will be very easy. Okay, okay, so this colored part is nothing but the compressed material. Okay, now just verify this colored part and your design of the product. Is it matching? It is matching. Okay, at the start this section is completely filled with this raw material. Okay, now by using this kind of punch, I am compressing it, and see, material is getting compressed around this side, at both this side and at the bottom, and I am getting the exact shape. Okay, obviously this is showing now, currently it is showing larger one, bottom part, this one, but but once it will be pushed inside this cavity, it will be compressed again, and ultimately you will get this part. Are you getting the things? Very easy. Okay, so just go on compressing, you will get exactly this kind of product. Okay, so now see, with the same base you cannot push it. For pushing or for pressurizing, for compressing, you need some larger base. Getting it? Okay, to apply the force, to apply the pressure, you need some larger base. And with this base and with this punch, I will show the punch with some different color. This is the punch. This is the punch. Okay, now just a minute, I have some message. Okay, so come back. Now this is the product you will get by using this kind of punch. So if I will remove the another part, okay, have you got the things now? I will remove this another part, and this is the our punch. Got the dimension? Have you got the dimension now? Sorry, have you got the design? This will be our punch. Okay, I have shown it by drawing the product also around it, how you will get the product. Okay, now what I want, forget about this top part. Which one? This one. This is nothing but the extra part which is just required for applying the pressure on the surface. Applying the pressure on the surface. Right, this is not a functional part, this is the requirement of structure. Getting it? Okay, and this is the exact part which will compress the material. Okay, now I want the size of this. I want size of this. Obviously this is not hollow, this is a solid part, simply solid cylinder. Getting right? Okay, so yeah, right. Okay, so this is the simple, this size of punch, so this is called as a punch. Now we want the dimension of this punch. Okay, so this punch is going to be inserted here, so we want this internal dimensions, we want this internal dimensions, As such, there is no any formula for calculations. Just a minute, I need to check one message. Getting okay. So here, just this product will be there. Okay, so this internal part of the product will be appear here. Okay, so this diameter I need first. So this diameter is nothing but the diameter of this inside one. I'll show it with some different color. Hold a minute. Okay, sorry for disturbance. Right, just let me check audio is okay. Okay, so this size of punch is nothing but the inside dimensions of this particular component. So what is the inside dimensions? The 4 centimeter is the length. Sorry, 4 centimeter is the total diameter. Out of this, you will have to reduce this uh, thickness of the component. Okay, just keep it in mind. This is a diametrical part. Okay, this is the diametrical part. So 4 millimeter, 4. This is not meter. 4 millimeter. Okay. 4 and 4 8, so total is what is it? Total is 4 centimeter. Out of that we'll have to subtract 0.8 centimeter. Have you got from where I have taken this 0.8 centimeter? This thickness of the component. Okay, so this exactly it will be 3.2 centimeter. Okay, so I am putting this 3 centimeter here. 3.2 centimeter. Got the thing? So this dimension is nothing but 3.2 centimeter. Okay, okay. Now can someone tell me what is going to be length of this punch or the height of this punch? What will be the height of this punch or the length of this punch? Diameter I have calculated. Okay, I told you how to calculate the diameter of the punch. Okay, but what will be the height of the punch? Okay, height of the punch will be effective only for this much. Okay, this red colored top part is not a functional part of the punch. This is only for pressurizing, okay, getting it? Okay, so see this effective length or height of the component, is 2 centimeter. Okay, this is a 2 centimeter. Okay, but now if you check this lower base part, so the punch is not going to pierce here. Okay, punch is not going to pierce. Okay, so it is not going to pass from this solid part. The movement of punch will start from this position. It will compress the material and it will reach to this part only at this level. Okay, and this below bottom part is a solid part. This is a solid base. So this movement will be from this top point to this one. Okay, so what is this thickness is 4 millimeter and total height is 2 centimeter. Sorry, thickness, total height is 2 centimeter and thickness of the part is 4 millimeter. Okay, thickness of the part is 4 millimeter. So just reduce the thickness of the part from this travel. I'll remove this one, you will understand it easily. Okay, 2 centimeter is the total height minus thickness will be minus 4 centimeter. So it will be 1.6, not millimeter, centimeter. It will be 1.6 centimeter. Okay, so this distance or this dimension, this is 1.6. This is the 1.6. Okay, so this height will, why it is coming millimeter, centimeter. But the thing, only 2 dimensions we required. Being a very simple component, the size of the punch, and the length of the punch. Okay, this is 3.2 centimeter and this is 1.6 centimeter. Okay, how we have gone for the reverse engineering. We know the product, we want only the size of the punch, and size of the punch is depending on the size of the component, okay, where it is going to compress. Okay, so that's how you will have to calculate the dimension of punch. Okay, so got it now. This I think this is the last one, right? Okay, so dimension of punch, length of ejector pin by using this formula L1, L2, L3. L1 is equal to 5 into dp, L2 is the stroke, L3 is a allowance. Clamping force, flash thickness, depth of loading chamber by using this formula, volume of loose powder, land dimension, projected area, and this volume of the product. Okay, so first part will be your calculation of volume of product. Okay, so these 9 sections are required. So these 9 sections are required for the design of compression component. Okay, sorry, compression mold. Okay, so that's how you will be able to design a simple compression mold product. Sorry, compression mold for the product given. Okay, so product, if suppose there will be and a problem based on this, so this kind of simple products will be given, and by you can easily calculate any kind of product or any size of product. Just a minute.